September 12th, 1943. Luftwaffe Maintenance Depot. Rechlin, Germany. Oberingenieur Friedrich Weber's hands trembled as he unfastened the inspection panel on the captured American bomber's wing root. What he found inside would haunt German military planners for the remainder of the war. Every component bore identical serial numbers, every rivet hole aligned perfectly with pre-drilled templates, every wire bundle terminated in standardized interchangeable connectors. The Consolidated B-24 Liberator, forced down nearly intact after a mission over Kiel, wasn't simply an aircraft. It was a manifestation of industrial philosophy that German engineers had dismissed as theoretically impossible. Weber, a veteran of Messerschmitt's design bureau with 17 years of aviation experience, had personally overseen the production of hundreds of fighters. Each one required skilled craftsmen, making countless individual adjustments, filing parts to fit, hand-forming metal to achieve proper alignment. The American bomber before him contained no evidence of such craftsmanship. Instead, every component suggested something far more terrifying than superior engineering. It suggested unlimited, automated reproduction. The B-24 had arrived at Rechlin 3 days earlier, escorted by armed guards and technical intelligence officers from the Reich Air Ministry. The aircraft had sustained surprisingly light damage during its emergency landing in a field near Hamburg. 2 engines damaged, landing gear collapsed, but the fuselage and wings remained structurally sound. German fighters had forced it down after flak had wounded the pilot and knocked out the number 3 engine. The crew, taken prisoner, had sabotaged what they could before capture, destroying the Norden bomb site and classified radio equipment. But they couldn't destroy what the aircraft itself revealed about American industrial capacity. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Weber had assembled a team of Germany's finest aeronautical engineers for the examination. Hauptmann Klaus Richter from the Technical Air Armament Department, Dr. Heinrich Schreiber from Juncker's Research Division, and Engineer Martin Hoffmann from Focke-Wulf's Production Planning Section. Together, they represented decades of experience in aircraft design, manufacturing, and tactical deployment. Their initial assessment, filed on September 14th, would circulate through German High Command like a virus, infecting every optimistic projection about the war's eventual outcome. The team began with external examination. The B-24D model, before them, measured 67 feet in length with a wingspan of 110 feet. Empty weight exceeded 36,000 pounds. Maximum takeoff weight approached 65,000 pounds, heavier than most German medium bombers fully loaded. 4 Pratt, 4 and Whitney R1800 twin Wasp engines, each producing 1,200 horsepower, hung from the wings in nacelles that showed sophisticated cooling design. But it wasn't the specifications that shocked the German engineers. It was the construction methodology. Hoffmann, responsible for production planning at Focke-Wulf, noticed it first. He was examining the bomb bay doors when something caught his attention. Every hinge bracket bore identical part numbers, not similar numbers, identical numbers. He called Weber over and pointed to a small, stamped marking. "Look at this. Part number 47329A. Now, look at the corresponding bracket on the opposite door." Weber examined the second bracket. Same number, exactly the same. He moved to another hinge assembly further aft. Same number again. "It's standardization," Hoffmann continued, his voice carrying an edge of concern. "But standardization at a level we've never achieved. These aren't just interchangeable within this aircraft. I'd wager these parts are interchangeable across every B-24 ever built." The implications were staggering. German aircraft production relied heavily on skilled labor making individual adjustments during assembly. 2 Messerschmitt Bf-109 fighters built in the same factory on the same day would have subtle differences in fit and finish. Components required careful filing, adjustment, and custom fitting. A replacement wing panel for one aircraft rarely fit another without modification. The system worked, but it required highly trained craftsmen and consumed enormous amounts of time. The American approach, as evidenced by the B-24, eliminated individual fitting entirely. Parts were manufactured to tolerances so precise that any component could replace any other identical component without adjustment. A mechanic in the field could swap parts between aircraft without specialized training or tools. More importantly, production could be distributed across multiple factories, even contractors, with no previous aviation experience, and the parts would still fit together perfectly. Dr. Schreiber, the Junkers researcher, discovered the next revelation while examining the wing structure. The B-24 used a distinctive, high-mounted wing design that Consolidated had designated the Davis wing. Extremely efficient at high altitude, it provided exceptional lift-to-drag ratio. But Schreiber wasn't interested in aerodynamic efficiency. He was studying the manufacturing methodology. "They've built this wing in sections," he announced to the team. "See here? The center section is one complete unit, built separately and then joined to the outer panels. Each outer panel is itself built as a complete subassembly. The entire wing can be constructed by teams working simultaneously on different sections, then joined together in final assembly." Weber understood immediately. Modular construction. Instead of building the wing as one continuous process, they break it into independent modules that can be built in parallel. "Exactly," Schreiber confirmed. "And look at these joints. They're not welded or riveted in the traditional sense. They're using flush riveting with countersunk holes, all pre-drilled to exacting specifications. The rivet spacing is absolutely uniform. No craftsman eyeballing the placement. This was done with templates and automated drilling equipment." Richter, the armament specialist, had been examining the aircraft's defensive weapons. He called the others to the tail turret. "Gentlemen, look at this mounting system. The entire turret assembly is a self-contained unit. It drops into a prepared opening in the fuselage and connects through standardized electrical and mechanical interfaces. No custom fitting required. A factory could build these turrets completely separately from the aircraft, and they'd install perfectly every time." The revelation continued as they moved through the aircraft. The electrical system used standardized connectors throughout. Every wire bundle terminated in identical plugs that could only be connected one way, preventing installation errors. The hydraulic lines used AN standard fittings, each size and type, identical across the entire aircraft and, presumably, across the entire American military aviation inventory. The oxygen system, the fuel system, the control cables, every component showed evidence of ruthless standardization. Inside the cockpit, they found more evidence of American production philosophy. The instrument panel used standardized gauges with identical mountings. A replacement altimeter from any American aircraft would fit perfectly. The control column, throttle quadrant, and rudder pedals showed no evidence of custom fabrication. These were stamped parts, formed by massive presses, identical to thousands of others. But it was inside the fuselage that Weber made the discovery that would fundamentally alter German understanding of American industrial capacity. He had removed an inspection panel near the radio operator's position and was examining the structural framework. What he saw made no sense, according to German manufacturing practice. The longerons, the primary structural members running the length of the fuselage, bore laser-straight rivet lines with absolutely uniform spacing. He measured the distances, every rivet hole exactly 1 1/2 inches from the next, for the entire length of the longeron. No variation, no adjustment, no evidence of human judgment in the placement. More disturbing were the stamped markings on the structural members. Each piece bore not just a part number, but also a date code, inspector's stamp, and manufacturer's mark. Weber recognized the manufacturer codes: Boeing, Wichita, Douglas, Tulsa. North American, Dallas. These weren't Consolidated's own parts. They were components built by other companies, completely different companies, yet they fit perfectly into this Consolidated-built aircraft. They're using multiple contractors, Weber said slowly, the full implication dawning on him. Different companies, probably hundreds of miles apart, building components that are so precisely standardized they can be assembled by yet another company without any fitting or adjustment. Hoffman pulled out a small notebook and began calculating. If they've achieved this level of standardization across contractors, they could expand production almost infinitely. They're not limited by the capacity of one factory or even one company. Any factory with basic machining equipment and proper tooling could produce components. The assembly could happen anywhere. Dr. Schreiber was examining the aluminum skin panels. Look at these markings. This panel was manufactured on July 23, 1943, 6 weeks ago. The inspector's stamp shows it passed quality control on July 24th. This aircraft was probably completed within days of that date. He pointed to the aircraft's data plate, accepted by the Army Air Force on August 1st, 1943, from raw materials to combat-ready aircraft in barely a month. Impossible, according to our production schedules. The German engineers spent 3 more days examining every aspect of the B-24's construction. They measured tolerances, documented manufacturing techniques, photographed details, and compiled a comprehensive report. Each new discovery reinforced the same terrifying conclusion. The Americans had solved the fundamental problem of mass production at a scale Germany couldn't match. The rivet holes told a particularly disturbing story. In German aircraft production, skilled workers drilled rivet holes during assembly, positioning each hole based on experience and judgment. The Americans had eliminated this variable entirely. Every hole in the B-24 was pre-drilled using automated equipment and permanent templates. The holes aligned perfectly because they were made by machines following precise patterns, not craftsmen making individual decisions. The flush riveting technique itself represented a manufacturing revolution. German aircraft still used primarily raised head rivets, which created drag but were faster to install. The B-24's flush rivets required countersunk holes and careful installation, yet they appeared throughout the aircraft. This suggested automated riveting equipment capable of installing thousands of rivets with perfect consistency. Weber discovered evidence of this automation in the wing panel seams. The rivet spacing was so precise, the countersinking so uniform, that no human hand could have achieved it. The Americans were using automated riveting machines, probably massive presses, that could install dozens of rivets simultaneously. German factories still relied on workers with rivet guns, installing one rivet at a time. The fuel tanks revealed another level of automation. Instead of building tanks custom-fitted to each aircraft's structure, the Americans had designed standardized tanks that fit into standardized bays. The tanks themselves showed evidence of automated welding, with seam quality superior to anything German craftsmen achieved by hand. Every tank bore test pressure stamps showing they'd been hydrostatically tested before installation. This wasn't just quality control. It was industrial process control that assumed perfect replication. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Richter's examination of the defensive armament system revealed tactical implications beyond manufacturing. The B-24 carried 10 50-caliber Browning machine guns in various positions: nose, tail, top turret, ball turret, and waist positions. Each gun was identical. Each used the same ammunition feed system. Each could be removed and replaced without special tools or fitting. A damaged gun could be swapped in minutes with a spare, unlike German defensive weapons that often required hours of adjustment after replacement. The ammunition system showed similar sophistication. Standardized ammunition cans, each holding specific quantities, fed the guns through track systems that prevented jamming during aircraft maneuvers. The entire system showed evidence of extensive testing and refinement. This wasn't a prototype or experimental design. This was a mature production system that had been debugged and optimized. The bomb release mechanisms demonstrated American precision manufacturing at its finest. The intervalometer, the device controlling bomb release timing, was a complex electromechanical computer that could calculate and execute release patterns, accounting for altitude, airspeed, and desired spacing. Yet it was built from standardized components that showed no evidence of individual adjustment. The device was designed to be replaced as a complete unit rather than repaired in the field, another indicator of abundant production capacity. As the examination concluded, Weber compiled the final report. His summary would circulate to the highest levels of German military command, eventually reaching Albert Speer, Minister of Armaments and War Production. The report's conclusion was unambiguous. The American aircraft industry has achieved a level of production automation and standardization that renders traditional craftsman-based manufacturing obsolete. Their ability to distribute component production across multiple contractors while maintaining perfect interchangeability suggests industrial capacity that may exceed our estimates by an order of magnitude. Most concerning is the implication that they can expand this production system almost limitlessly. We are not facing a larger version of our own industrial system. We are facing a fundamentally different approach to manufacturing that we cannot match with current methods. The report included detailed photographs, measurements, and technical drawings. Weber had documented everything from rivet patterns to wiring harness routing. But the most damning evidence was simple. The small stamped markings on components showing they were built by contractors scattered across America, all fitting together perfectly in an aircraft assembled in San Diego, California. German intelligence had already reported on American production facilities. The Willow Run plant near Detroit, built by Ford Motor Company specifically for B-24 production, occupied a single building covering 67 acres. The main assembly line ran nearly a mile in length. Reports suggested the plant would eventually produce one complete bomber every hour. German analysts had dismissed this as propaganda. No factory could achieve such production rates for something as complex as a four-engine bomber. But examining the B-24, Weber realized the reports might be accurate if components were standardized to this degree, if sub-assemblies could be built simultaneously by different teams or even different factories, if final assembly was reduced to joining pre-built modules, then the production rates became theoretically possible. Not easy, but possible for a nation with America's industrial base and resources. The cockpit layout revealed another American advantage: ergonomic design based on pilot feedback rather than engineering convenience. The controls fell naturally to hand. The instruments were arranged logically, grouped by function rather than scattered randomly. The throttle quadrant operated smoothly with positive detents for common power settings. This wasn't accidental. American designers had clearly studied human factors and incorporated pilot preferences into the design. German aircraft were built to engineering specifications, with pilots expected to adapt to whatever arrangement resulted. Hoffman examined the landing gear mechanism with growing dismay. The entire assembly was a self-contained unit that could be removed and replaced in hours rather than days. The retraction mechanism used commercial hydraulic components, simplified versions of systems used in American trucks and industrial equipment. German aircraft used custom-designed hydraulic systems that required specialized knowledge to maintain. The American approach traded theoretical efficiency for practical maintainability, another indicator of production-focused thinking. The environmental control system showed similar philosophy. Rather than optimizing for minimum weight and maximum efficiency, the Americans had designed for reliable operation and easy maintenance. The oxygen system used standardized regulators and fittings throughout. A mechanic could rebuild the entire system using parts from supply without worrying about compatibility. The heating system used simple exhaust heat exchangers that could be replaced without special tools. Weber's final inspection focused on the data plates throughout the aircraft. Every major component, every subassembly, every piece of equipment bore a small metal plate with manufacturing data. Part number, contract number, manufacturer, date, inspector's initials. The systematic documentation suggested quality control processes that tracked every component from raw material to installation. German factories attempted similar documentation, but inconsistently and without the systematic rigor evident in the American aircraft. The captured B-24 represented more than just enemy technology. It represented an industrial philosophy that German engineering culture had difficulty accepting. German tradition valued the skilled craftsman, the master technician who could hand-fit parts to perfection, who took pride in custom work and individual achievement. The American aircraft embodied the opposite approach: remove the craftsman from the equation entirely, replace skill with precision tooling, substitute individual judgment with automated process control, eliminate adjustment through perfect standardization. As Weber prepared to leave Rechlin, he took one final walk around the captured bomber. In the fading afternoon light, the B-24 looked almost crude compared to German aircraft. The riveting, though precise, lacked the smooth finish of handwork German construction. The paint application was adequate, but not artistic. The overall aesthetic suggested functional utility rather than engineering elegance. But Weber now understood that these apparent deficiencies were actually strengths. The Americans weren't trying to build beautiful aircraft. They were trying to build thousands of adequate aircraft faster than Germany could destroy them. And based on what he'd discovered, they were succeeding beyond anything German planners had imagined. Weber's report reached Albert Speer's desk on September 21st, 1943. The Minister of Armaments and War Production read it twice, then summoned his chief aviation production advisor, Dr. Wilhelm Messerschmitt. What followed was a meeting that would fundamentally reshape German understanding of the industrial war they were losing. Speer spread Weber's photographs across his desk, each image showing another example of American production automation. Messerschmitt examined them in silence, his expression growing darker with each page. "Can we replicate these methods?" Speer asked directly. Messerschmitt's answer would be recorded in his post-war memoirs. "Technically, yes, we understand the principles: precision tooling, automated drilling, standardized components, modular assembly. We've known these concepts for years, but implementing them requires something we don't have: time, resources, and a complete restructuring of our entire manufacturing philosophy. The Americans didn't develop this system for the war. They developed it for automobile production in the 1920s and 1930s, then adapted it to aircraft. We would need to rebuild our entire industrial infrastructure. It would take years we don't have. We don't." Speer pressed the issue. What if we focused on one type, stopped producing 5 different fighter models, and concentrated everything on perfecting production of one design? "We tried that with the Me-109, Messerschmitt replied, "but even our most streamlined production still requires skilled labor at every stage. We lack the precision machine tools the Americans use. Our factories are built around craftsmen, not assembly lines. Converting would mean months of retooling, during which production would cease entirely. We can't afford that disruption." The conversation revealed a brutal truth that German leadership struggled to accept. The war wasn't being lost, because of inferior German technology or courage. It was being lost because American factories could produce adequate aircraft faster than German factories could produce superior ones. Quality had become irrelevant when facing overwhelming quantity backed by relentless standardization. The numbers told a story of industrial annihilation. By the time Weber examined the captured B-24 in September 1943, Consolidated and its contractors had already produced over 4,000 Liberators. Ford's Willow Run plant was approaching its design capacity of one bomber per hour. Douglas in Tulsa, North American in Dallas, and Consolidated in Fort Worth were adding hundreds more monthly. Total B-24 production would eventually exceed 19,000 aircraft, making it the most produced American military aircraft in history. German four-engine bomber production told a different story. The Heinkel He-1-77, Germany's primary heavy bomber, numbered barely 1,000 aircraft total production across the entire war. The Focke-Wulf FW-200, an excellent design, managed fewer than 300 aircraft before production ceased due to resource constraints. Germany never achieved the industrial scale necessary to compete with American production capacity, but the B-24's impact went beyond mere numbers. The standardization that Weber had discovered enabled a maintenance and logistics system that German forces could never match. American bomber groups, operating from England, received regular shipments of spare parts that fit any aircraft in the fleet. A damaged wing could be replaced with one built 6 months earlier at a different factory. Engines were swapped in hours rather than days. Battle damage that would ground a German bomber for weeks could be repaired overnight on an American aircraft. Lieutenant Hans Kruger, a Luftwaffe maintenance officer stationed at a bomber base near Munich, witnessed the disparity firsthand when his unit received a captured B-24 for evaluation in early 1944. His diary entries, discovered after the war, revealed growing despair as he compared American and German maintenance capabilities. "We spent 3 days fabricating a replacement hydraulic line for one of our He-170s, custom bent tubing, hand-fitted connectors. 3 skilled men working constantly. The American bomber uses standardized lines throughout. Their mechanics simply disconnect the damaged line and install a replacement from stock. 10 minutes work. We're not fighting an air force. We're fighting a factory that happens to have wings." The psychological impact on German aircrews was devastating. Oberst Werner Baumbach, commander of a bomber wing, described the hopelessness in a 1944 report. "We destroy one American bomber and 3 more arrive to replace it. Our crews see this. They understand mathematics. When we lose aircraft, replacements arrive eventually, maybe. When we lose experienced crews, they're gone forever. The Americans lose crews and new ones appear within weeks, fully trained, flying factory-fresh aircraft. Our men are brave, but courage cannot defeat limitless production." The American training system represented another advantage that the captured B-24 inadvertently revealed. The aircraft's design philosophy assumed average pilots and mechanics would operate it. Controls were simplified, systems were redundant, maintenance procedures were documented in detailed technical manuals that any competent mechanic could follow. German aircraft were designed assuming expert operators. This worked well early in the war when Germany had those experts. By 1944, the experts were mostly dead. Technical Sergeant James Mitchell, a B-24 crew chief with the 8th Air Force's 93rd Bomb Group, exemplified the American approach. Before the war, Mitchell had worked as a garage mechanic in rural Kansas. His aviation training consisted of 8 weeks of technical school and 4 weeks of on-the-job training. Yet, by mid-1944, he was maintaining complex 4-engine bombers under combat conditions with casualty rates approaching 20%. "The manuals told you everything," he later recalled. "Step-by-step procedures, torque specifications, troubleshooting guides. You didn't need to be a genius. You just needed to follow instructions and have the right parts. We always had the right parts. German maintenance, by contrast, relied heavily on experienced mechanics, using judgment and improvisation. This worked brilliantly when those mechanics were available. But as casualties mounted and experienced men were transferred to training units, desperately trying to produce more aircrew, field maintenance quality deteriorated. The American system of documented procedures and standardized parts didn't require experience. It required compliance with established processes, something that could be taught quickly to anyone with basic mechanical aptitude. The strategic bombing campaign revealed the full horror of American production capacity. Operation Point Blank, the combined British and American offensive against German industry, saw hundreds of B-24s and B-17s striking targets across occupied Europe daily. By mid-1944, German fighters and flak exacted terrible tolls. On some missions, loss rates exceeded 10%, but the bombers kept coming. Wave after wave, their formations filling the sky like mechanical locusts. Hauptmann Josef Fischer, a Luftwaffe fighter pilot with 43 confirmed kills, described the futility in a letter to his wife intercepted by Allied sensors. We shoot them down. God knows we shoot them down. Yesterday, I personally destroyed 2 of the big 4-engine machines. Direct hits, both burning, both crews killed. I felt nothing, no satisfaction, no pride, because tomorrow there will be 4 more, and next week, 40 more. They keep coming. Our bullets kill their crews, but bullets cannot kill American factories. I think we are fighting an enemy that cannot be defeated by courage alone. The statistics bore out Fischer's despair. In 1944 alone, American factories produced over 16,000 4-engine bombers, split roughly between B-24s and B-17s. German industry produced approximately 30,000 aircraft of all types that same year, but most were fighters designed to counter the bomber offensive. The strategic mathematics were brutal and unavoidable. Germany was trading expensive fighters and irreplaceable pilots against bombers that America could afford to lose. The human cost on both sides defied comprehension. American bomber crews faced casualty rates that exceeded those of infantry soldiers in the worst ground battles. The 8th Air Force alone lost over 26,000 men killed and another 20,000 wounded. The life expectancy of a B-24 crew member during the peak of the bombing campaign was estimated at 15 missions. A full tour required 35 missions. The mathematics was simple and terrifying. Yet the crews kept flying because the replacement pipeline never stopped. Training bases across America graduated thousands of pilots, bombardiers, navigators, and gunners monthly. The B-24's standardized design meant that crews trained on one aircraft could immediately operate another. No adjustment period required, no custom familiarization needed. Climb in, run the checklist, fly the mission. American industrial philosophy had reduced even human operators to interchangeable components in a vast machine. German aircrew faced different mathematics but equal terror. By late 1944, Luftwaffe fighter pilot life expectancy was measured in weeks, not months. Training had been abbreviated to dangerous levels as fuel shortages limited flying hours. New pilots arrived at operational units with less than 100 hours total time, expected to face American fighters and bombers crewed by men with 3 or 4 times their experience. The veterans who survived knew they were simply delaying the inevitable. Lieutenant Friedrich Weber, the engineer's nephew, flew FW-190 fighters against B-24 formations in the spring of 1945. His combat reports, preserved in Luftwaffe archives, revealed the desperation of final months. Attacked bomber formation at 1300 hours. My cannon struck the lead aircraft repeatedly. I saw pieces flying from the wing. The bomber continued in formation, apparently undamaged. Either my guns are worthless or these machines are indestructible. I think the latter. We are shooting at ghosts made of aluminum and steel that absorb our fire and return it tenfold. The younger Weber was shot down on March 15th, 1945, by a B-24 waist gunner. He survived with severe burns and spent the war's remaining weeks in a military hospital. After Germany's surrender, his uncle Friedrich visited him, bringing photographs from the Rechlin examination. The younger man studied the images of the aircraft that had nearly killed him, tracing the rivet patterns his uncle had documented 18 months earlier. "You tried to warn them," the pilot said quietly. "You told them what we were facing. They didn't listen." The elder Weber shook his head. They listened. They understood. But understanding changed nothing. We didn't have the tools, the resources, or the time to match American production methods. Some problems can't be solved with engineering brilliance or tactical skill. Some problems can only be solved with factories, resources, and time. We had none of those in sufficient quantity. The post-war accounting revealed the full scale of American industrial achievement. A total B-24 production reached 19,446 aircraft. They were built at 5 different final assembly plants by thousands of contractors supplying components. Peak production at Willow Run reached 1 bomber every 63 minutes. The plant employed 42,000 workers at maximum capacity, most of them women with no previous industrial experience. They assembled aircraft from components built by suppliers scattered across the American continent, every part fitting perfectly because precision tooling had eliminated human variation. German engineers examining American factories after the war were stunned by what they found. Dr. Schreiber, part of the original Rechlin examination team, visited Willow Run in 1946 as part of a technical intelligence mission. His report described an industrial process that seemed almost biological in its relentless efficiency. Components arrive continuously from hundreds of suppliers. Sub-assemblies are built on feeder lines feeding the main assembly line. The main line moves constantly. Aircraft move from bare fuselage to combat-ready bomber in progressive stages. We saw aircraft in every stage of assembly simultaneously. The process never stops. One bomber completed, the next already taking shape. This isn't manufacturing as we understood it. This is industrial reproduction. The captured B-24 that Weber had examined at Rechlin survived the war. American forces recovered it when they captured the research facility in April 1945. The aircraft, battered from German testing and examination, was eventually scrapped, but its legacy lived on in the thousands of technical reports, photographs, and analyses it had generated. German engineers had documented every aspect of American production methodology, creating a comprehensive blueprint of industrial practices Germany could never implement. Albert Speer, interrogated after the war about German industrial failures, pointed to the B-24 examination as the moment German leadership understood they were fighting an unwinnable industrial war. We could match American technology. We often exceeded it. Our jets were faster, our rockets were more advanced, our submarines were better designed, but we couldn't match their production system. They had perfected the art of making adequate weapons in unlimited quantities. We pursued perfection in limited numbers. History proved their approach superior. The irony was profound. German engineering, celebrated for precision and quality, had been defeated by American engineering, celebrated for standardization and quantity. The craftsman culture that produced beautiful, individually fitted aircraft couldn't compete with the assembly line culture that produced adequate, perfectly interchangeable aircraft. Quality had lost to quantity, not because quality didn't matter, but because overwhelming quantity made quality irrelevant. The B-24 Liberator's combat record reflected this philosophy. It wasn't the best American bomber. The B-17 Flying Fortress was more rugged. The B-29 Super Fortress was more advanced. But the B-24 was adequate for its mission, and could be produced in quantities that overwhelmed any defense. That adequacy, multiplied by 19,000 aircraft, achieved strategic victory that superior German designs couldn't prevent. In 1985, Friedrich Weber attended a reunion of Rechlin technical staff in Munich. The surviving engineers, now elderly men, gathered to remember their wartime service. Someone brought photographs from the B-24 examination. Weber found himself staring at images he'd taken 42 years earlier, seeing them with the clarity that only decades of reflection could provide. "We were looking at the wrong thing," he told the group. "We documented the standardization, the automation, the precision tooling. We understood the manufacturing implications, but we missed the deeper truth. American industrial culture was fundamentally different from ours. We believed in the master craftsman, the skilled expert who could solve any problem through individual brilliance. They believed in the system, the process, the documented procedure that any trained person could follow. We couldn't adopt their methods because doing so would have required abandoning our entire cultural approach to manufacturing. We weren't defeated by better technology. We were defeated by a different philosophy of production that we couldn't accept and couldn't match." The audience listened in silence. These were men who had designed some of the war's most advanced aircraft. They had created jets while America still relied on propellers. They had built rockets while America struggled with short-range missiles. Yet they had lost because excellence in isolated examples couldn't defeat adequacy in overwhelming numbers. Weber continued, his voice carrying the weight of understanding earned through defeat and reflection. "That bomber we examined represented something we had never encountered. Not a weapon, but a manifestation of industrial capacity so vast it could afford to be wasteful. They didn't hand-fit parts because they didn't need to. They had precision tooling that eliminated fitting. They didn't rely on skilled craftsmen because they had systems that made skill unnecessary. They didn't optimize for efficiency because they had resources to be inefficient. We were fighting on our terms, trying to maximize the output of limited resources through brilliance and skill. They were fighting on their terms, accepting adequate results multiplied by unlimited resources, and their approach won." The final accounting of the B-24's impact went beyond production numbers or combat statistics. It represented a transformation in warfare itself. Industrial capacity had become as important as tactical brilliance or strategic vision. The nation that could produce more adequate weapons faster would defeat the nation producing fewer superior weapons. This lesson, learned at terrible cost by German forces, would shape military thinking for generations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.